So take it away.
Thank you. So good morning, everyone. Thank you all for coming so early in the morning. I know it's difficult. I find it difficult too. So today I'm going to talk about designing a chronographic system. So it's going to be interesting. I'm going to show you probably that's quite difficult, that we need to do a lot of stuff. So let's get into it. So one of the things that we often talk about this week, it's contrast. So we all talk about contrast the whole time because we're always doing direct imaging, so we're searching for contrast. However, contrast is not well defined because when we talk about contrast, what do we actually mean? Do we mean the instruments contrast? Do we mean astrophysical contrast? Do we mean contrast after some type of normalization? We're not always very careful about what we mean with contrast. So if we're talking about what sets the fundamental limit for high contrast imaging, then we usually specify a contrast. For example, if we take a G2 star and Earth, then we say it's about 10 to the minus 10. But if we're talking, for example, about an M star and Earth, then it's like 10 to the minus 7-ish. So that's an astrophysical oriented contrast. But then if we talk about instrumentation contrast, then we might talk about extreme adaptive optics, the raw contrast after an AO system, which is 10 to the minus 4, maybe 10 to the minus 6. Or we might be talking about post-processed contrast, which is 10 to the minus 6 to 10 to the minus 7. So it's a bit random in the end what speakers usually mean with contrast, because there's all these different terms. So if we are talking about contrast, and we are actually hitting a sort of a problem, because contrast has many different meanings. So it's always very good to specify it. But then there's a fundamental thing by just talking about contrast. And that fundamental issue is that contrast is not a noise model, because it's just some type of sensitivity that we reach. For example, if you have a perfectly static background, you could just subtract it out because it's perfectly static. It's static for infinity. For an infinite amount of time, you subtract it out, it's gone, and there's no problems. For example, if you have a perfect aberration-free PSF, then it's just a background that you subtract. And here I can show it. So this is an image of a star with a planet PSF in it at about 10 lambda over d at a contrast of 10 to the minus 10. My PSF is completely static. It's aberration-free. I can subtract it out. I change the color bar, as you can see here, and there's my planet. So if we have a static background, it's really easy. We just subtract out its static background. So why do we need a coronagraph at all if we can do this? It's pretty easy. So one of the problems, the first problem that we encounter, it's actually quantization of the electric field. So Eva did a really good talk earlier this week, where she showed us that the intensity that we measure is the absolute value squared of the electric field. So this tells us we can take images. Like I showed you before, we take the image, we subtract the PSF, and we're done. However, roughly 100 years ago, people came up with quantum mechanics, and they figured out the electric field is actually quantized. So here you can see the second quantization of the electromagnetic field. You don't have to remember these equations because we're not going to use them. But from these, we actually derive that photons, or at least the electromagnetic field, comes in discrete packages, which we call photons. And when we add this, it actually becomes very difficult, because now I am generating different images with different amounts of photon flux, so different amounts of photons per frame. So on the left, it's 100. In the middle, it's 10 to the 5. On the right, it's 10 to the 10 photons per frame. So now if we run the movie, you can actually see what that photon noise does, or that discretization of the electric field. It causes us to, So you can see on the left, it's going to be very difficult to do any type of static background subtraction. So if we subtract the perfect PSF again, as what I did in the beginning, to get rid of starlight, we actually see something like this, where on the left, it's barely subtracting anything because we get single photons. In the middle, it's already a little bit better, but there's still a lot of noise. And on the right, we can actually see a planet. But that planet is only at a contrast of 10 to the minus 5. And we used about 10 to the 10 photons. So if there's anything that you need to remember about photon noise is that it reduces by the square root of the number of photons that you image. So if you want to do 10 times better, you need to get 100 times more photons. And that's pretty tough scaling. So signal to noise. This is the noise that we have because this is the amount of photons that we get from the star, where this is the amount of flux from the star, the integration time, and then KSP is the raw contrast from the star at the position of the planet. So that's just the fraction of light from the star that hits the patched area where the planet is. And then we can actually calculate a signal to noise. So we have signal to noise here. Signal is, of course, this thing is difficult. There. So we have the signal of the planet, which is just the flux of the planet times the integration time, divided by the square root of the number of photons from the star. That's our signal to noise. So signal and noise. Okay, so if that sets our noise limit or our signal to noise, how long does it take to see an Earth-like planet with a perfectly diffraction limited PSF? And I'm assuming a 6.5 meter aperture. And I want to have a 5 sigma detection limit. So that's what I'm showing here. So this is the contrast curve of 1 second. So is there maybe someone that wants to make a guess on how long it will take to actually go to 10 to the minus 10 to search for an Earth-like planet within 6.5 meter aperture? What was the first one? 1,000 years. You are correct. It takes it takes about a millennium to average out the photon flux to find a 10 to the minus 10 planet around a 0th magnitude star with a 6.5 meter aperture. So this is the problem. This is the fundamental problem why we need a chronograph. Because we will never be able to search for an Earth-like planet if this is our noise. And I think this is one of the most important things to think about when you design a chronograph system. You need to think about your noise. In the end, you need to build up a noise model of your optical system, of your observations, and figure out how can I get rid of the noise? Which noise terms can I actually modify and which are fundamental? So in this case, photon noise is a fundamental noise. We cannot do anything about it except try and remove the photons. So that's what we do. That's why we build a chronograph. So here we use a perfect chronograph that perfectly removes the starlight. We look at the 10 to the minus 10 planet with a 6.5 meter aperture, and we can detect it in about 15 minutes. There it is, with photon noise in it from the companion itself. It's really easy. And this is then also a fundamental limit set by astrophysics. Because in the end, if we have a perfect chronograph that perfectly removes the starlight, we're limited by the photon noise of the companion itself. Because the planet also sends out discrete photons, of course. So you still need to capture enough light from the planet that you get a high enough signal to noise. However, we will never have a perfect system, of course. So we need to do our best to make it as perfect as possible. So what are the sources of error? Well, this week we already talked a little bit about aberrations. So anything that modifies the state of the wavefront will introduce a stellar leakage into the chronograph. And that means that the instrument environment matters. So if we can talk about different types of telescope, you have ground-based and space-based telescope who have different, like these two have, of course, different environments that they work in. So that means that for these two different systems, if you do high contrast imaging on the ground or you do high contrast imaging in space, you get different error budgets because there are different wavefront errors that will fold into the noise. So for example, if you have a telescope and an instrument and there's some type of vibration, and we look at like how does the vibration impact the vortex chronograph, then on the left, you can see the vibration that I put in. So that's the wavefront error map. You can see it's tip or tilt. I mean, in this case, it's purely Y, but it will move. And on the right, we can see the residual of the vortex chronograph. And when we run that tip tilt, you can see that the vortex pattern is just jittering around. And it's actually causing a lot of light that leaks around the chronograph. Okay, this is still not a super big problem. if we can actually do perfect PSF reconstruction. So if we have a perfect model of that vortex pattern that we then subtract, then we're only left by the residual photon noise. However, if we have an imperfect PSF, so we don't exactly know the vortex pattern, then we subtract a wrong pattern, and then we are left with what's something we call speckle noise. So in this, of course, this doesn't remind you of the speckles that we see in the actual data, and that's because this is only tip-tilt, and in actual data we have way more wavefront errors. However, when I run this simulation, if you do perfect subtraction, you can actually see that the photon noise averages out, and we can actually go and dig deeper. But when we do the imperfect PSF subtraction, then it doesn't average out that well. We keep all that light, all that leakage, we keep seeing it. So one of the most important things is to think about not only like what are the things that leak into the chronograph, but what's my measurement? What type of measurement am I doing, and how does that impact my noise sources? So you can actually not design your chronograph without knowing what type of measurement you're taking, because the different types of measurements change your noise budget. Okay, so first of all, let's check what the impact of wavefront aberrations are. So we're going to do some math. So at the top, I'm showing the electric field. It's pi times e to the I phi, which is just the pupil function times a phase aberration. And if we have small wavefront errors, which we typically have in space-based applications, for example, then you can actually make a Taylor expansion. So we make a first-order expansion. And the first-order expansion of the complex exponential is 1 plus I phi. Well, then we say, let's suppose there's a chronograph, and this chronograph actually removes the fundamental mode, the piston mode. So we have a really good chronograph that perfectly removes it. Then we're left with whatever leaks through. So those are phase aberrations. But this is in the pupil. Then we do a Fourier transform, and what we get out in the end is just the Fourier transform of the pupil times the aberration, times I. But this is just a scalar, so it doesn't matter. And then in the end, our intensity in the focal plane is just the absolute value squared of the Fourier transform of our aberration across our pupil. So that's pretty abstract. So let's try to analyze it in OPD instead. So OPD is optical path difference, and that's usually like a deviation in height. So we can go from OPD to phase, and we do that by doing 2 pi times the height of the aberration divided by lambda. So for example, this height can now be like 1 nanometer, 10 nanometers, 100 nanometers. And then delta here is just the shape of the aberration, like a sinusoid, like we discussed yesterday. If we take out these constants, because we can take out constants, we see that the intensity in the focal plane scales with 4 pi squared times the amplitude of the aberration squared divided by lambda squared. And so there's already 2 important scaling relationships that you now noticed for chronographs. Is one, it scales with lambda to the -2 squared. So that means if you make your wavelength twice as long, your contrast will be 4 times better. So that's an important thing to remember. And another one is how it scales with aberrations. So we see that the intensity in the focal plane scales with the aberrations amplitude squared. So if you are able to reduce your aberrations by a factor 2, you gain a factor 4 in contrast. So these are just important things to keep in mind, because they help you to do back of the envelope calculations when you want to try and scale your system. Like suppose we do 10 times better, then you can sort of guess how much better in contrast you will do. We can also plot this. So if we make this assumption, we look at the power, and then for a sinusoid, we for like a sinusoid aberration, then this Fourier transform amplitude, if you integrate it over the spectrum to just get a feeling for how much power there actually is in your focal plane, then that integrates out to about the order unity, because a sinusoid has order unity power, and the Fourier transform of it also has unity power. That's Parsifal's theorem. So that means that roughly the contrast in your focal plane roughly is 4 pi squared times the amplitude squared divided by lambda squared. So we can actually fill that in and pick like 700 nanometers or 750 nanometers. We like that wavelength because it's the wavelength where we can detect oxygen. And And then here you can see we have the wavefront aberration in nanometers versus the contrast that we are achieving, like the contrast that the aberration has. And then if we look here, we're at 10 to the minus 10, we can actually see we need on the order of picometer wavefront errors to achieve this 10 to the minus 10 contrast. So it's pretty tough. And that already gives us our first consideration when we design a chronograph system, and that's the deformable mirror. So here you can see a deformable mirror from the paper from Garrett Ruane. And when we control electronics or we control anything in the lab, we need to use a digital analog converter because we have bits in our computer and we need to convert those bits to a voltage signal. And that means you go through this digital analog converter that changes bits in a voltage signal so that you can actually control actuators. And those have a certain bit depth. So it means you have a precision. And due to that precision, and that also means that the values are actually quantized. You cannot arbitrarily change the height of your actuator because of the quantization error. And that means you have actually limited accuracy on the surfaces that we can apply. So here you can see on the left the ideal surface that we want. In the middle, we have the surface with the errors, and on the right, you have the difference. And you can see that the difference is actually on the order of a tenth of a nanometer in this case of the DM. So is that important? Well, we just told ourselves that we need to have picometer precision. So yes, it is important. And here you can see the effects in actual lab results where they made a dark hole in the chronograph. And on the top, you can see the quantization error of the DM, like how big are the steps. And you can see it has pretty big impact in the contrast of the dark hole. Even 0.2 nanometers is enough to just be at roughly the 10 to the minus 8 level. So this is already the first aspect of a high contrast imaging system. We have not even done anything complicated. We just said, let's suppose we have a chronograph and a DM. That is already giving us a lot of problems. So there are also way more sources of wavefront error. So here I'm listing some. We have telescope vibrations, thermal deformations of the telescope of the instrument, internal wavefront errors, chromatism between maybe the channel that we're using to sense the wavefront and the actual science that we're using. And then depending on your environment, depending of if you're on the ground or in space, you also have different types of wavefront errors. On the ground, we have the atmospheric turbulence. And then a big one that we almost never discuss because we all don't like it's atmospheric dispersion. So because the Earth is round, and when light enters the atmosphere, it actually gets refracted at the space-Earth interface. And that causes a lot of problems. We have dome seeing. In the IR, you're actually hit by varying water vapor content. And of course, we have thermal backgrounds because the Earth is hot. So the atmosphere is also hot. And I call it hot, but we need to, if you cool down your instrument to like 80 Kelvin, then a thermal background of 290 Kelvin or 270 Kelvin is pretty hot. In space, we have way different issues. Well, in EVO, some of them are common, but for example, one that we learned with James Webb is that we have micrometeorites that can actually impact your wavefront error budget. There's changing thermal radiation because you can get different angles that the instrument is making with respect to the sun. So that means that depending on how the sun illuminates your instrument, you get different thermal radiation. You might have degradation of the telescope coatings over time, which you cannot fix because the telescope is in space. And we also need the picometer stability requirement to do the coronagraphy, which is all complicated. So when you actually design a system, you need to make an error budget. Like I said before, we need a noise model. Without a noise model, you can actually not decide whether or not something is better than something else. So that's why we need to make a contrast budget. So here I just sort of split it up in 3 terms. Of course, there are way more, but in like I like to think about these. So we have astrophysical noise that will be added, which is something we can barely do anything about. For example, the star has a certain stellar angular diameter. We cannot do anything about that. The star is just that size, and it's at a particular distance. Star brightness. A star has a particular brightness, so that means there's a certain amount of photons that will come in, which is important for wavefront sensing and control. There's exozodiacal dust, which was shown yesterday. And the other thing which is also important is there's unknown orbital motion of the planet that you're looking at. So if you do very long exposure times, for example, you need hundreds of hours to detect a planet, which is actually what we're thinking about. It could well be, especially for nearby systems, is that these planets are actually orbiting around their star. So it's actually non-trivial to figure out which photons and which signal, where on the focal plane do we need to add them together to actually get that detection. So orbital motion is also an unknown. And that will also fold into our contrast. Then we have wavefront errors. I mean, I already showed a couple, but here I'm just highlighting them. In the end, we also have detector noise. I skipped the detector, but detector noise is, of course, also an important thing. We have read noise, dark current, charge transfer noise, detector saturation, and all those effects also play into part when you design your chronograph. So we can almost do nothing about the astrophysical noise because that's just astrophysics. That's what the universe gives us to work with. We can try a little bit harder on unknown orbital motion by doing precursor missions, like we do radial velocity missions or maybe astrometric missions to try and constrain orbits. But actually, the other things, there's barely anything we can do about it. I mean, a star is a star and it's there. For the middle part, we can actually try to do wavefront sensing and control, and we can try and improve the performance, or we can improve the stability of our instrument. And on the other last part, we can try and develop better detectors. But we're slowly hitting actually the limits of what detectors can do for us, because we're now hitting the limits where we can do single photon detection. And when you can do single photon detection, there's almost very little what you still can gain, because we're almost at hitting the actual limit. So let's start with wavefront errors, because I can talk a lot about that. I will start a little bit with ground-based errors. Yesterday it was already shown. We have atmospheric turbulence, and this atmospheric turbulence comes from convection in the atmosphere. So you have cool air that comes to land. The hot land heats it up. The air goes up in the atmosphere, and then it cools down and goes down again. So this is a very local effect. So locally on the atmosphere, locally on Earth, depending on your conditions on top of your mountain or wherever your telescope is, you have different types of convection and different rates. And then there's also global convection things like the Hadley cells. And it's these two things together that cause convection of air, caused by differences in temperature of these turbulence cells. And that atmospheric turbulence is then created, or at least the turbulence created by the convection, and this creates pockets of air with different temperatures. And if you have a different temperature, that means you have a different refractive index. And if you have a different refractive index, then you have a different wavefront aberration. So that's actually the fundamental thing that causes atmospheric seeing. It's temperature differences throughout the air, and also spatially varying temperature. And then it creates images you can see here on the right, which is pipe up observed with MAGIO-X in just natural seeing. And you might not notice it, but there's actually a companion star in this image. If you're very well trained, you might actually be seeing it. You might actually see it now, but it's difficult. So what we do adaptive optics. It was already discussed a little bit yesterday. We have aberrated light coming in, hitting our mirror. We take an image, and then it's seeing limited. We see a blob. Okay, so the first thing we need to do, we need to add a wavefront sensor. We need to measure the state of the wavefront to control it. Then we send it off to a real-time computer that decides, oh, this is the wavefront. How should I optimally control our DM? Then you send some feedback, and then you suddenly have a PSF. It's pretty nice. We can get high resolution images again. However, you can see it's still a little bit of a mess. But if we do that on sky, then we can actually transform our seeing limited PSF into a diffraction limited PSF. So here you can now actually see the companion star, which is here. And then there's lots of other stuff happening, which is all due to your system, which is why your contrast budget is system dependent. And you need to think about it. Okay, so let's dive a little bit deeper into wavefront errors for the atmosphere. All wavefront errors have a particular lifetime. And that means that instead of thinking about square root n scaling or square root t scaling, like you average out with taking more integration time, you actually have to think about that speckle lifetime. So instead of scaling as square root t, it scales as square root t over tau, which is the speckle lifetime. So the lifetime of how long a wavefront aberration lives really matters for your detection limits. And also matters for how well you can sense it in the end. So if you look at this and think about how well do my speckles average out and what's the impact on our noise budget, then you get something like this. So here on the right, you can see the integration time versus the variance of the mean. So this is sort of the noise. And you see two different curves, with one with a normal controller, the other one with predictive control. But you can see that both of them in the beginning don't really average out. It takes a while for them to average out until it starts to become longer than the typical lifetime of your speckle. So what sets the limits of high contrast imaging? It's this speckle lifetime and the speckle amplitude. So understanding only your amplitudes is not enough. You also need to know how long they will live. So you can actually write down that error budget. So here it is. Yeah, it's pretty intense. And this error budget, again, depends on the type of measurement. So here I am assuming that I can subtract a PSF and that I'm left with random speckles that average out. So this, again, is a noise model for a particular type of measurement. So it contains of a lot of components. The first one is just flux, which is good, which is not that difficult. But then all the other ones are complicated. So we have the green parts that are caused by the static diffraction pattern of the instrument that will live for a very long time because that's just your instrument. That could even be the residual pattern. And then we have the long-lived quasi-static speckles. So those are speckles that live for about a minute to hours. And then we have the short-lived atmospheric speckles, which are about 5 milliseconds to 100 milliseconds. So we have these three terms. And they all interact with each other, and it's all very disappointing. It's difficult. So how can we improve our limits? We either reduce the speckle strength or we reduce their lifetime. So both of them will help us in improving our contrast. And active wavefront control actually reduces all the terms. It reduces the intensity, but it also reduces the speckle lifetime. So we should always think about active wavefront control. It will save our life. So, but can we arbitrarily speed up wavefront sensing and control? The answer is no. Because within a typical lifetime of a speckle, you can only collect so many photons. And that means that, again, photon noise hits us. And that means there's a certain precision of your measurement. And that means you are balancing things first between correction speed, which you see on the left, the purple part, and on the right, we have the measurement noise. So you need to balance your measurement precision versus how fast you can correct the speckle. And this is very, very difficult. So here you can see an image where this is an on-sky sphere image. And here the speckles live for a very long time. And then we can control them very well, so we don't see the speckle halo. If we have a short coherence time, so here the speckles live very shortly and we run at the same speed, you can actually see that they create this blur of light. So thinking about how long your speckles live and how well you can control and at what speed you control really matters for your contrast budget. So speed matters. So suppose that we can actually do very well. We are in a situation where the speckles live for a very long time. What sets the limit then? Well, it's the long-lived quasi-static speckles. So you need to do something about those. And we can do that with focal plane wavefront control. And these quasi-statics actually originate usually from within the instrument. So this is an image of MagioX, which is a high contrast imager. And the blue part that you see is the science part. So those are the light rays that go to the science camera. But at a certain point, we need to split them off to do some type of wavefront sensing. That's where the purple rays start to come from. That's the wavefront sensor part. You can see that they are going through different sets of optics. So it means that in the end, they are actually measuring different wavefront errors. And that's what we call non-common path errors, because they're not in a common optical path. And that's what generates these quasi-static speckles. And also the reason why they live on long time scales is because they live, they're generated by changes in the instrument. And changes in the instrument go very slowly when the temperature changes, when maybe the gravity factor changes. So you have slow changes. But they create a lot of aberrations. So here you see a chronographic image of MagioX. And we can see that there's actually a lot of speckles that diffract around the edges. they cause stellar leakage, and they reduce our performance. And because they change slowly, they are actually difficult to remove with post-processing. Because if something changes maybe 2 or 3 times across your observation sequence, then the best that you can do is to average it out by a square root 2 or square root 3. So it's actually very difficult to suppress them if they slowly change. It's extremely annoying. But like I said before, active waveform control is the thing that saves us. But if you have an AO system with a deformable mirror, who will win the AO control battle? Is it the wavefront sensor that tries to correct atmospheric turbulence? Or is it the wavefront sensors that try to do focal plane wavefront control? So you need to think about implementing your system and think about like how they actually interact with each other for the different purposes in your instrument. So what we did at MagioX, we just added another deformable mirror, just add a couple more degrees of freedom and make sure that each thing does its own thing. And with that, we are actually able to do focal plane wavefront control. And here you can see us doing focus diversity. So we just apply a couple of defocused images, and it allows us to actually remove some of these non-common path errors on this separate DM. So this is also on-sky data. And then on Sky, we are actually able to get really good PSFs. On the left, you can see our aberration corrected PSF, and on the right, you can see our theoretical model. So they match up very well. And then the other thing is, for example, focal plane wavefront control to create these dark holes that we've seen a couple times during this conference. So this is really focused on getting rid of these quasi-static speckles that live there. So before there are lots of speckles, we do some type of focal plane wavefront control, and then we can actually remove a lot of these quasi-static speckles. Some of them still are there, but this was the first time we ever tried it. So I think we did a good job. So if you remove the quasi-static speckles, what's the next limit that you hit? Well, it's the atmospheric speckles again. So they're back. And that's one of the things that we're reaching in high contrast imaging, is that it's constantly this battle against noise limits. You remove one noise limit, then another thing becomes a new noise limit. And we are constantly just switching around, figuring out like what's our new noise. So this is the full equation for what I said before. Like we do imaging where we try to subtract a PSF model, and it's not always perfect, so we get speckles. If you're able to do photon noise limited post-processing, so that means that's the first one that I showed, where you can subtract a perfect copy of your PSF or of your speckles, then you can actually remove a lot of these additional terms which are caused by interference. And then we have photon noise limited post-processing, or signal to noise, or noise in this case. But then we need to think about the efficiency of the photon noise limited post-processing technique, because you might throw away 95% of the light and retain 5% to do your post-processing. However, in how you improve here is the only thing you need to do is reduce speckle strength. And still here, active wave control still reduces the speckle noise. So in ground-based systems, we're usually speckle noise limited by the atmosphere. In space-based systems, we're usually sort of photon noise limited. I mean, it's not completely true, but let's assume it's true. Then we can do some typical integration types. So residual speckles at the 10 to the minus 5 level with a coherence time of 10 milliseconds, planet contrast of 10 to the minus 8, means it takes about 70 hours for us to reach that planet at 5 sigma. A space-based limit, we have 10 to the minus 10 raw contrast. We're searching for a 10 to the minus 11 planet, because we all say that Earth is 10 to the minus 10, but it's actually secretly a couple times 10 to the minus 11. And if we search for it around a 5th magnitude star, we also arrive at a roughly 70 hours of exposure time. So finding planets at high contrast just takes on the order of several tens to 100 hours of exposure time. That's how long a single target takes. Which is also why mission design and survey design is very important, which is what the rest of the talks of today will be about. So where are we currently? Here is a plot created by Vanessa Bailey, and I've added the targets that we want to observe with GMagioX, which is one of the instruments we're developing, which are all these triangles. So these are all radial velocity detected planets. And those are the ones that we try to image. And these are also in reflected light. So currently, we can do about this contrast. With MagioX, we're trying to do a lot of performance improvement to actually get this flat 10 to the minus 7 contrast. And why do we want to do that? It's because we want to image Proxima Centauri b, which is purple over there. So Proxim b is our favorite target. Should be everyone's favorite target. It's our nearest neighbor, so we at least want to know what our nearest neighbor looks like. So if we fill in actually what we think we can do with the extreme large telescopes and the space-based telescopes, then the ground-based ELTs can image this part of the planetary regime. So we get about 10 to the minus 8 because we are limited by these atmospheric speckles. And then space-based like Hab worlds can actually do this part because Hab worlds has better sensitivity, but it has a smaller inner working angle because it's a smaller telescope. So they are very complementary in types of reflected light planets that we can actually access, which is good. So are there more speckle origins? So here I'm just going through a history of speckles. So we have differential NCPA between on-sky and internal source. So I told you before that the quasi-static speckles are created inside the instrument. Well, they change when you calibrate them off-sky and on-sky. So if you do your daytime calibration and think, I've made a perfect system, and you go on-sky, then suddenly there are aberrations that start to appear. We have the low wind effect, which is a new thing, where if the wind is drifting very slowly across your aperture, then you think, well, that's great because the atmosphere barely moves. Well, it's actually not great. It creates a lot of issues, which is the low wind effect, which you can see here. So it's sometimes also called the Mickey Mouse effect because it creates a Mickey Mouse type PSF. You can see it here with its face and its ears. Not great. We discovered about this like about 7-9 years ago. Then we have polarization aberrations. So I did not talk about polarization at all, but each polarization state propagates through your system in a different way. And it means that there's a difference between the different polarizations. So here you can see images from Sphere and GPy where we can actually see the effects. We can actually see the effects that they create here and here. Then we have a lot of vibrations. So this is a typical power spectrum of the Scaxio telescope of Subaru with the Scaxio instrument. And you can see on the left that there are lots of frequencies that the telescope creates. We have lots of different vibrations and they change in time. So on the y-axis, you see time, and on the x-axis, you see the spectrum, and you can see they change. It's very complicated for small inner working angle coronagraphs because this is the dominant error. And these are telescope dependent, and you don't necessarily know them before you have built your telescope. So that means you can also not prepare your instrument for it, which means we have an unknown. There are chromatic wavelength errors. So here you see the contrast as function of wavelength. You can see in the middle design wavelengths were pretty fine. We have pretty deep contrast. But then you go out of your center wavelength and then suddenly the contrast starts to become worse. And that's because we have wavelength errors that have chromaticity. So we're now slowly going towards the era of the ELTs and Hab worlds. We are getting huge telescopes, 40-meter class telescope, 30-meter class telescopes, great. But they are very complicated. So we're developing a high contrast imaging system for the Giant Magellan telescope at Arizona, which is GMAGIO-X, the Giant Magellan Adaptive Optics Extreme instrument. And it's complicated because we're building new telescopes. They're all segmented. We're getting new errors, such as phasing errors. So here you can see that these telescopes are segmented and they create a new type of differential piston. So each segment has a different phase. So we need to co-phase the segments to create a good PSF. So to deal with that, we're designing the GMAGIO-X wavefront sensing and control block diagram, which you can see here. So we have 9 deformable mirrors in GMAGIO-X to make sure that we can do everything we want. And we have many different control loops that are talking with each other. So these are all things that you have to consider. We go through all this error budget nonsense. We think of all the errors that can happen in your system, and then you try and design active wavefront control elements that can correct for those errors. And then you get very complicated schematics. So later this week on Friday, Dr. Jared Mills will talk about the actual design of GMAGIO-X. So you can ask him for all the details. So in conclusion, you really need to make a noise model to understand which aspects limit your observations. and how they impact your instrument design. And for that, you don't not only need to know your instrument, but you also need to know the type of measurement you're taking. So you need to know how the data will be reduced, because that sets the type of noise budget. Active wave control will always improve sensitivity. And I think it's the main path forward for more efficient wave planet imaging. And also the stability of our instruments really limit our performance in post-processing. So more stable instruments are better. And in the end, what I want to leave you with is there are no free lunches. Instrument design is always a trade-off. You will never be satisfied with the instrument that you build. Thank you.
Wonderful. Thank you. That was very interesting. No, unlike any questions in the room? Okay. Please. I'll run it over.
Hi, that was a really good talk. I was thinking a little bit more about the phasing errors you mentioned. So this is something that Keck also goes through, like every time there's a segment exchange and having to balance the phases between the segments. And so I was wondering how phasing errors change when the diameter of the primary scales up, and if there's something to do with actuator design and the segment support that can somehow or slightly mitigate phasing errors.
Yeah, so the question is like, how do the phasing errors change when you go to bigger apertures? And the question is, luckily they don't change too much, because atmospheric turbulence has a sort of, we call that outer scale. So that's the biggest type of turbulence cell that will drift across the telescope. And that typical outer scales is somewhere between 10 and 50 meters. So that means when you have a telescope at 10 meters, that outer scale doesn't really change anymore, because you sort of hit that outer scale limit. So bigger telescopes will, at least from the perspective of the atmosphere, will not have significantly different temporal behavior or amplitude behavior, because we've hit that outer scale size. The segments themselves, like mechanical phasing, is different, because mechanical phasing depends on how you actually optomechanically have combined the segments and what type of actuators you put behind it. And that's challenging. I think based on the experience we now have with Keck and with the Gran Telescopio Canarias and the Canary Islands, we actually have good ideas about the type of sensors we need at the edges of the segments to actually make sure that they don't lose shape.
Okay, thank you. Any others? If not, I'll ask mine. Okay. So in a situation where you are co-designing your telescope and your chronograph at the same time, trying to optimize a single starlight suppression system, which is what's happening for Habitable Worlds Observatory, or beginning anyway. Mm-hmm. What's your general advice in a case where we can, in fact, try to make the telescope match the chronograph in advance?
Yeah, that's a good question. I would say it's actually very complicated, because you need to, so like I said, you first need to start writing down your error budget. And I think that's the first thing you do, is like you think of all the types of errors that can happen during a measurement. And then you need to see how you can change them. So the first thing is really think about everything that can happen, which is complicated. And then you write it down, and then you can see how the telescope impacts the errors. Then you see how the chronograph design impacts the errors, and then you need to change them. So you can do it as a sort of an integrated system optimization. But then we can also think about, like, suppose that we can just define, maybe the errors don't interact with each other. That would be the best case, because if the errors don't interact with each other, that means we can design the system separately. And then you can just optimize the telescope separately from the chronograph. So sadly, it's not completely the case for Habitable Worlds. So we need to do sort of an integrated modeling. I don't have the answer for that. It's just a lot of work, long years.